Okay, so good afternoon, everyone. Welcome to this Friday quantum seminar webinar. Today, I'm very pleased to introduce Professor Vincenzo Savona. Vincenzo is based at the EPFL in Lausanne, where he heads the theoretical physics of nanosystems department, and he's also the director of the EPFL Center for Quantum Science and Engineering, which is very interesting because we are setting up a Center for Quantum Science and Technology in Stellenbosch. I've started interacting with Vincenzo not so long ago because we both engaged with GESDA, the Geneva Science and Diplomacy Anticipator, and were involved in the activities that led to the foundation of the Open Quantum Institute, which is a kind of a global initiative based at CERN to give access to quantum computing to everyone. And we're also working on trying to show that quantum computer can solve some real-life problem. And in particular, we try to find algorithms to optimize how the food system chain works and might be able to be optimized. Yeah, but that's probably a talk for another time.
Well, but it's related, and I will mention this.
Okay, fantastic, excellent, fantastic. Okay, but today he will speak about optimization problems with variational quantum inspired algorithms. Yeah. So Vincenzo, thank you very much for agreeing to give this talk. We are very happy that you are with us. And please, you know the rules of the game.
Yes.
You have to press the green button.
Yes, absolutely. Let me just start the presentation and share
maybe while you do that, maybe a reminder to the participants, if you have a very, very urgent question, you can ask it during the talk, choosing maybe a little bit of a tactful moment, but otherwise we can leave a discussion to the end of the talk. Yeah. So Vincenzo, we can see your slides.
Yes, now you should see
perfect. Now it's full view.
Yes,
perfect.
Full screen. Yes.
Thank you very much.
Okay, so thank you very much, Francesco, for this very nice introduction and for the opportunity to give this to present this result. What I'm going to talk about today is a very recent activity that we started in my group, which concerns optimization and physical inspired optimization algorithms. It's a new topic which I am getting very much interested in, and as I'll tell you in a moment, there is also a strong connection to the work that we are doing together with Francesco and with food scientists for the Open Quantum Institute. Okay, I want to acknowledge from the very beginning the fantastic work done by my PhD student Lorenzo Fioroni, who's the student who's in charge of this research line, and he was very quick in producing interesting results. So I'm very grateful to him. So I will be talking about optimization. This is the outline of my talk. I will first of all let me just start a pointer so that I can point. So I will introduce what optimization is, and then I will talk a bit about the physics-inspired optimization algorithms. And then I will introduce the algorithm that we have developed and describe its features and show with some numerical experiments his advantage. And then I will conclude and draw and give you my outlook. So what is an optimization problem? It's very simple. You are given a function. It's a function of a variable which typically is made of many. It's a large dimensional space, and in useful applications, these variables can be of different nature. Some of them can be real. Some of them can be integer numbers, and they need to be integer. They can't be relaxed as real numbers. And typically the number of these variables is very large, okay? And what you want to do is that you want to find the particular point in this multidimensional space which makes this function minimal or maximal, depending on how you have defined your problem, okay? And typically these problems come with additional constraints. So the question that you ask is, can find the point that makes this function the smallest, for example, while fulfilling some constraints. This is wrong here. There should be an equality, not an inequality. What I meant here is that some constraints come in the form of inequalities and some in the form of equalities. So these are additional constraints that your variables have to fulfill. Okay, and this problem, I mean, this is the most, this is the general illustration of the problem. And typically, this problem, in most cases, is NP-hard. NP-hard means, to make it simple, that if you, to the best of what you can do, the time to solution, the time it takes to find the minimum is exponential. So scales exponentially with the number of variables. Okay, and this is known and very rigorously proven for most specific cases of these optimization problems. Optimization comes a little bit everywhere. Here I had fun at compiling a long list of all the fields where optimization has a great impact. And I mean, I found there are some review papers. The literature is really vast. That it's even difficult to redirect towards a set of papers because. The reason is that optimization is necessary in the most diverse fields, going from engineering to environment to healthcare, medicine, energy, all fields of engineering, and as I will show in a moment, also agriculture, and but also economy, public policy, and so on. So, so this is why this problem is very important. Let me give you a couple of funny examples. For example, apparently Amazon is saving millions by optimizing the routes of the people who are delivering the packages, that are the Amazon packages. And this is a kind of optimization which resembles the famous traveling salesman problem, which is what is the shortest path that touches at least once all cities on a map. And this problem, however, is more complex than the simple traveling salesman problem, because the transporters, they have to fulfill delivery time windows that exist because of several constraints. And they have also to account for real-time traffic data for the localization of the various service providers and so on. So it is a really complex optimization problem that must be run almost in real time. The current research being led by Amazon requires these things to be run in tens of seconds, in 10 seconds. And this can lead to a huge saving. And it is called online optimization, not because it is on the internet, but because it is run almost in real time. Okay, so what do we learn from here? We learn that optimizing an optimization problem, it's very difficult to define a metric to estimate the quality of a given approach to optimization. It may be that you can find a very good solution, but that it takes forever, or it may be, and perhaps it's better to find an approximate solution in a much shorter time. And it is very difficult to define what is actually the metric to the figure of merit of a given approach to optimization. Another example is exactly what we are working on together with Francesco. The idea is that, so we are working on this for the Open Quantum System, for the Open Quantum Institute, sorry, Freudian lapsus. essentially, the idea is that you have geographical regions, typically in developing countries, where you would like to optimize food production, in particular agricultural production. And you want to optimize a number of different things. This is a multi-objective optimization. You want to optimize, you want to maximize the profits of the local producers. So you want to minimize waste. You want to minimize environmental impact. You want to maximize the food quality. So, for example, storage must be limited to the time that is allowed for a given kind of foods before they are spoiled. You want to maximize the nutritional power of the diet, so to make this region as autonomous as possible. And you want to minimize social aspects like economic injustice that is perceived by farmers. And there are many other requirements. A very nice paper, which is an original result, but also a review of what has been done, is this very recent paper that I'm quoting here. And this is also very significant because it shows you how, if you start writing a model to account for all these things, they do this for a specific problem, a use case, which is the production of tomatoes in Argentina, in a region of Argentina, and they end up with an optimization problem which has essentially 100,000 variables of all kinds, and 300,000 constraints. So you can understand how this problem becomes very, very large and difficult to treat immediately. Remember that the complexity to find the optimal solution is exponential in these numbers. So this is going to be really impossible, okay? At least to find the absolute extremum of this function. Yeah, exactly. We are working together with the Open Quantum Institute, which was founded by JESDA and is now an independent institution located at CERN. And this problem that we're working on is part of a number of problems that are being addressed by the Open Quantum Institute. The dream is to use quantum computers. And we would like to contribute to the sustainable development goals that have been set by the United Nations very recently. You can find a lot of information on the link that I'm providing here. And yeah, exactly. This is the collaboration that I had prepared here. We are working with the Global Alliance for Improved Nutrition, which is exactly the institution that helps us understanding what are the issues to deal with in this food problem, because there are very, very good food scientists in there. Okay, so one would like to say, okay, let's all focus on trying to find the best optimization algorithm ever. But apparently this is not a good idea, because there is a quite famous theorem which is called the no free lunch theorem. To cut long story short, this theorem says there is no general optimization approach that performs best in all cases. Each kind of optimization problem comes with some specific structure that is more suited to be addressed with the one algorithmic approach rather than with another. So there is no best. Okay, it depends a lot on the problem that you are going to solve. And the bottom line of this is that whatever effort that finds new strategies for optimization may bring large benefits, even though it's not the best, because by definition, according to this theorem, there is the notion of the best optimization algorithm is ill-defined in itself. And this is a little bit the motivation of our work. How do we measure the quality of an approximation? Well, of an optimization, since it is impossible to compute the true minimum of a function, and probably we will not even need it, typically one searches for approximate solution. Approximate solution means the following, that the optimal solution, I call it X naught. You find the solution. Suppose that you want to maximize the f, you find a solution which is not the maximal, but it is not much smaller than the maximum. So this ratio is going to be close to 1. And essentially, this ratio, the ratio between the value of the function for this approximate solution that you have found and the true optimum, is called the approximation ratio. Okay, and you may want to quantify the performance of an optimization algorithm, of an approximate optimization algorithm, in terms of the size of this number. So how is this number is close to 1? Okay. However, as I said before, you can do that, but another parameter is the time. Okay, you may have algorithms that find good approximations in a short time, but you can have algorithms that find much better approximations, but require considerably longer time, and in some cases you may prefer the first one to the second. Now, given this definition of approximate optimization algorithms, there are actually two classes of such algorithms. There is what we call approximate optimization algorithm. This is something which has where the algorithm has a guaranteed approximation ratio. What does it mean? It means that given the kind of problem to optimize, you know that given an approximate optimization algorithms will find a solution which will be at least which will be close to the optimal solution by at least a given number, which is a given approximation ratio, which is a feature of the optimization algorithm itself. Okay, an example for this is the Goeman-Williamson algorithm for max cut problem, which has an approximation ratio of close to 0.8 or something. So it means that whatever instance of the problem you give it, it will always find a solution which is at most 20% for which this value of the function is at most 20% from the actual solution. Then there are algorithms which are called the heuristics, which are also approximate algorithms, which do not have a guarantee. So essentially, this algorithm will give you an approximate solution, which is typically good, but you don't even know how close you are to the optimum. Okay, and the prototypical example of this is the simulated annealing that I will be describing in a moment. And these two, these heuristics are typically the simplest algorithms to implement, and also those that admit a physical implementation, and therefore they are typically the preferred solution when you have to optimize problems that are NP hard and that are very large. So starting from now, we will be talking about heuristics. There are some commercial solutions for optimization in general. These two very famous commercial optimization softwares, they are not heuristics. They attempt to solve to find the true optimal solution. They are quite famous and used everywhere. You also have hardware optimizers, and something that I like very much is the perhaps less known Fujitsu digital annealing unit, the digital annealer. This is essentially an FPGA. For those who know a little bit of electronics, it means that it is a programmable electronic circuit. And this can be programmed in a way so that it can execute the simulated annealing. Okay. The advantage is that since it is a hardware, algorithm, it will be very fast. And in fact, these chips are very powerful. They can solve problems up to hundreds of thousands of binary variables quite easily. And this is just to explain that there are a lot of opportunities to solve an optimization problem, including ones based on physical implementations. So I want to talk about a very general kind of optimization, which is the quadratic unconstrained binary optimization. Well, faced to this very complicated name, this class of problems is very simple because it is essentially the Ising spin glass. Okay, so it is a problem corresponding to a classical Hamiltonian, where you have a lot of spin variables, classical spin variables, so variables that can take values plus minus 1. And you can essentially, you have some external field term, and then you have an interaction term, which is a spin-spin interaction, a pairwise interaction, okay, with some interaction coefficients which form a matrix, sometimes called the adjacency matrix. And both these numbers and the external field, they are typically, I mean, they describe the specific problem that you are optimizing. Why is this interesting? This is interesting for two reasons. First of all, because a lot of optimization problems can be mapped efficiently onto QUBO problems. Okay, so there is this famous paper that says that when you have an optimization problem of another kind, you can transform it into a QUBO problem at a computational cost that is not exponential, but is just polynomial. So it is a sort of a universal problem, if you prefer. And also, it is interesting because once you have this problem, there are a lot of ways in which you can solve the QUBO problem with physics-inspired heuristics, so physics-inspired algorithms. Okay, and here I'm listing some famous ones: simulated annealing, quantum annealing, of which I'll be talking in a moment, and also these quite famous coherent Ising machines, also called simulated bifurcation machines. You can find information about this in these two papers here. What is simulated annealing? Simulated annealing is a physics-inspired algorithm where you imagine that your system is at a finite temperature, which we call T, and the idea is the following: you generate a random configuration of the spins. You start from a large temperature, okay? And then the idea is that you propose now randomly a new state. So starting from this configuration, you propose a new configuration. And if the configuration has a lower energy, then you will accept it and you will iterate this process. If the configuration has a higher energy, then you will accept it only with a probability which is given by the Boltzmann coefficient obtained by taking the energy difference between the starting and the end point, so between these two configurations. And you will only accept it with this probability here, if the energy is higher, okay? And this is mimicking the process of a system that is held at a temperature T, and which approaches thermal equilibrium. And you cycle, so you iterate this process, and during the iteration, you very slowly decrease the temperature. So at the beginning, with large temperature, this quantity will be very large, and so you will accept a lot of moves that actually increase your energy. But this will make it possible to overcome barriers and to find the minima of your function. And if you make the temperature go to 0 very slowly, okay, then you can in principle get to the absolute minimum of the function. But this will take an exponential time, because this problem is per definition NP hard, so it will be exponential. This algorithm is very, very simple to write. Actually, you can, I played the game, I asked ChatGPT to write it for me, and it came out perfectly. So it could run out of I mean, I did copy paste and it ran. It's very simple to write, and it's also very efficient because it is order of n square, where n is the number of binary variables. However, it can be not very efficient, as I will show you with our numerical experiments. A very famous solution, a very famous approach that has emerged with quantum technologies is what we call quantum annealing. In quantum annealing, you take, well, first of all, the problem that we want to solve now, I mean, I didn't include the constant, just the interactions. And now we are supposing that our classical spin variables transform into quantum spin operators, which are, however, in the z direction. So it's the z component of the spin, and as such, I mean, if you operate on this basis, say this is still a diagonal Hamiltonian. Okay, in terms of quantum physics, you would say, okay, this is diagonal, so it's already solved. But in practice, even only computing the energies and finding the smallest one on the diagonal is very difficult because diagonal is exponentially large. Okay, this requires a lot of time, a lot of memory, and a lot of calculations, because you have to compute the energies by carrying out this sum. Okay. So what quantum annealing does is that it prepares the state in the product state of the eigenstates of the X operator. Okay, so this is 0 plus 1 as a state, and then you take you engineer a system to have the Hamiltonian HI multiplied by time, divided by a constant. Now T is no longer the temperature, but it's a fixed time. And then you sum another term, which is called the driving term, and which is essentially an Hamiltonian that is just the sum of the X operator, the sigma X operator on all spins. And typically what you do is that you make, over time, you make this term become larger, and this term correspondingly becomes smaller. Now, at time equals 0, the Hamiltonian will just be this one. And as we said, this state is an is the ground state of this Hamiltonian, because here there is a minus sign. Okay. If this is the case, then by slowly evolving time, so if this end time is very large, okay, then the system will adiabatically stay in its ground state. And at the end of this annealing schedule, we will find ourselves in the ground state of the Hamiltonian that for which we are searching the minimum. Okay, so this is a typical example of adiabatic calculation that should bring you to the absolute minimum of this Hamiltonian. However, that's exactly what I said. However, what is the problem? The problem is that when you go along this evolution, the energy levels of this Hamiltonian here, which is now no longer a classical Hamiltonian because there is a field along X, and here there are operators along Z. So essentially, this is now a quantum Hamiltonian with non-trivial quantum states that are highly entangled at intermediate times. What can happen is that the eigenstates of these Hamiltonians, of this Hamiltonian here, have eigenenergies that come very close to each other, okay? And typically one talks about the minimal gap being the minimal energy level splitting between the actual ground state and the first excited state of this Hamiltonian along the annealing schedule, okay? And what you can show, there is an adiabatic theorem that tells you that this algorithm will only work if the time it takes to anneal is much larger than 1 over delta squared, where delta is this minimal gap. And as a matter of fact, this makes it very difficult to assess whether quantum annealing has an advantage for global optimization, because it will depend a lot on how this minimal gap scales with the size of the system, okay? Still, you expect some advantage, and just 2 days ago, I saw an article published on Scientific Reports where they provide numerical evidence for quantum advantage of the quantum annealing, or rather of the digital version thereof, which is the quantum approximate optimization algorithm, for a given problem which is considered of this kind, which is considered quite hard. How this works intuitively is that if you have a minimum and you start from a given state which sits in a minimum of your multidimensional potential, over time, in the end, the potential changes its shape because the Hamiltonian is evolving in time, is a time-dependent Hamiltonian, and at some point you go through a state where you have a quantum superposition of several classical solutions, which possibly explore the various minima of this potential landscape in a parallel way because of quantum superposition. We know that this notion of quantum parallelism is a stretch because in reality, because everything will depend on how slow you perform this process. Otherwise, you will go to occupy excited states and the adiabatic approximation will no longer hold. But in principle, this is the intuitive advantage of quantum annealing over classical annealing, is the fact that you can explore the various minima of the potential landscape in parallel because of quantum superposition. It's difficult to do this physically. First of all, because you need quantum mechanics, and you have seen that the interest is in solving the problem with hundreds of thousands, possibly millions of variables. Okay. One famous machine that does this is D-Wave. D-Wave, you can look at this very, very recent D-Wave publication that has a quite good account of what they did in the past. But D-Wave does essentially this. It's a superconducting architecture with qubits that interact with each other according to a given graph, which is called the chimera graph for the old machine. Now this new one has a new connectivity graph. But essentially this machine does the trick. It does it, so it does quantum annealing, the real one, the physical one. It does it at very small but finite temperature. It has been demonstrated that the scaling is what you would expect from quantum annealing carried out at a finite temperature. So it's not quite the same thing as what we have seen there, which is supposed to be at 0 temperature, but it works. And actually today, if you D-Wave offers a commercial solution where it takes your optimization problem, decomposes it into sub-problems. There is this divide and conquer strategy, and then the sub-problems are sent to the D-Wave machine, and then there is a classical algorithm that sews back all the sub-problems into the solution of the main problem. And this is a very good, it has one of the best performance that has been benchmarked. It has been benchmarked among the commercial solutions of this kind. So many people try to simulate quantum annealing classically, and the goal to simulate quantum annealing, so that the reason is that they want to understand how quantum annealing works. So the typical way to do that is by representing the quantum state along the annealing schedule variationally. So it means in terms of parameterized ansatz, which depends on a polynomial number of parameters. And then you apply the variational principle. So you try to minimize the quantum annealing Hamiltonian at each time over the parameters, which will give now a time-dependent schedule for the parameters. And ideally, if you do that, at the end of the annealing schedule, your parameterized wave function will approximate the actual quantum annealing state at the end of the schedule. So essentially, this is an approximation. As I said, the true solution evolves in Hilbert space, and your parameterization, since it is an approximation, will evolve close to it, but on a manifold, which is the one that is defined by the parameters. Okay. You can have calculations like this with hundreds of thousands of parameters. There are the most advanced numerical techniques to simulate this use a large number of parameters with a tensor network or neural network variational representations. But very recently, there were a few works. Here I'm citing one, but actually there were 3 works that arrived to the same conclusions. You can do something which apparently seems very strange. You can say, okay, let's take quantum annealing and let's simulate it using a mean field ansatz. So by introducing the mean field approximation. Mean field approximation means remove quantum entanglement completely. So assume that there is no entanglement. Assume that at each time, the states of the different spins are quantum mechanical. So they're defined on the Bloch sphere. But the overall state is separable, okay? And this is very simple to write. It's 2 lines of calculations, and it's very simple to write on a classical computer. And it turns out that this mean field approach results in an approximate, so in a heuristic, so in an approximate optimization algorithm, which is very efficient. It works very nicely, as I will show you in a moment, okay? And this is strange because we started with the idea that quantum annealing works because of the high entanglement in the intermediate part of the annealing schedule, and then we see that a mean field approximation of quantum annealing actually works very nicely. And so we had the following thought. So let's imagine on this axis you have the quality of how you represent the actual quantum state. Okay, here on this extreme is the actual quantum state, which requires exponentially many complex numbers to be represented. On the other side, there is the mean field approximation, which requires only order of n parameters to be described. Now, what happens is that all people are trying to simulate quantum annealing. They want to simulate it to best reproduce the quantum features in order to understand how quantum annealing works. And so they all work in this region, close to the full quantum state. Our idea, what motivated our work, is the following. Since the mean field approach gives a quantum-inspired optimization algorithm that is quite efficient, why don't we try, instead of putting as much entanglement as possible, why don't we try to put as few entanglement as possible and try to improve on this existing algorithm? And this was the main motivation of our work. So we are introducing a variational representation that contains just a little bit of entanglement. And by the way, it is very versatile and also tunable in a sense. And we use it to essentially write a new optimization algorithm. And as I will show, this performs significantly better than the mean field approach. Okay. So we will have some quantum correlations and entanglement in here, but the representation is such that we still have a decent, so an acceptable scaling of the complexity of this approach as a function of the number of variables in the problem. Now, so this becomes slightly technical for one slide. I will describe how this works. So the variational ansatz that we use is based on an ansatz which is called generalized atomic coherent states. And it's essentially given by the following. You start from the annealing state with all pluses, which is a product of all plus. And now you first apply a unitary, which is essentially separable. So these are single spin rotations with some parameters, okay? And you apply this. So essentially you rotate each individual spin while still keeping the separable nature of the state. Then you apply an entangling unitary, which essentially it's an exponential of with ZZ terms, okay, where these are other parameters, which will be varying for the optimization, okay? And this is just a pairwise correlation, and you apply as many, ideally, as the number, as the pairs of spins in your problem. And finally, you apply another unitary of this kind, okay? And you have now this parameterized state. What are the features of this parameterized state, and why do we use this instead of the most popular tensor network or neural network? Well, the reason is that the reason for using this state is that, as it has been shown in this and in some previous works, is that computing the loss function, so the function that you want to minimize, which is the expectation value of the Hamiltonian at each time, in order to carry out our optimization schedule, computing this is analytical. So it admits an analytical formula. It doesn't require any Monte Carlo sampling. It can be written analytical. It's just a linear algebra, and it typically requires order of n-cube operations. Okay. The same is true for the gradients with respect to the parameters. And this is very important because being able to compute these four quantities analytically makes it very, very quick to actually apply the annealing schedule and to run our simulated quantum annealing, which we do using gradient descent, like in many variational applications. Okay, so this is the idea. So you see here there is some entanglement, but still this is not. This leads to quantities that can be computed with simple linear algebra. And that do not require Monte Carlo sampling, which takes a lot of time and carries a statistical error. In order to extract the classical solution, because the final state will be a quantum state, this is a variational state. So nobody says that at the end of the annealing schedule you will be left with the classical state. Okay, what you can do is a very rough procedure, which consists in taking the expectation values of the z variables and taking the sign. So essentially, if a quantum mechanical spin is oriented a little bit on one side, it will give you a 1, and if it's oriented a little bit on the other side, it will give you a 0. And this is not very good, because this is perhaps the weakest part of this algorithm. That you may have configurations like this where the 4 possible results are quite ambiguous. Okay, so this can be misclassified by this technique, and there are some refined discretization schemes that extract the classical solution from the quantum state. One is the one used in this work, which applies another quite famous and promising strategy to optimizing these problems, which is called the approximate message passing algorithm. It's a class of algorithms that are used also to optimize QUBO problems. Okay, so as I said, the optimization requires order of n-cube operations. But now there is an advantage here, that we can, here in these ansatz, so we can decide which pairs of spin are actually coupled by this unitary. So if you set all the couplings here to 0, all the parameters of this entangling unitary to 0, then you recover the mean field ansatz, and the complexity is order of n squared. If you keep all of these parameters, then you have an order of n cubed. And now you can choose to make some of these parameters 0 and some not. And so essentially you can tune the complexity from n squared to n cubed together with the quality of your optimization. Okay. And for example, you can do two things. First of all, you can have optimization problems where the interactions are only local. And in this case, you may want to have the parameters here non-zero, only corresponding to the pairs of spin that are actually interacting. This is an approximation because these terms represent entanglement, and these terms represent instead coupling. And entanglement can arise also when two spins are not coupled, because there are spins that are coupled to both of them. And so entanglement can arise also between spins that are not directly coupled to one another. Or you can have systems that are all-to-all coupled. And in this case, you decide to apply an approximation. The matrix, the coupling matrix is full, and you take the entangling matrix and you keep only the parameters that correspond to the largest values of this coupling. These are heuristic approximations that lead to interesting results and that are only and that make it possible to lower the number of parameters, so to almost continuously tuning from n cubed to n squared. Okay, let me give you some results, and then we are finished. We have benchmarked this approach on 4 models. The first is the Sheridan-Kirkpatrick model. It's a model where you have random couplings between all pairs of spins. So each pair of spin has a coupling with a random coupling strength. And the coupling strengths are distributed as a Gaussian. Okay. And here I'm showing the average over a large number of instances of the problem. Okay. I'm showing the results of 4 algorithmic approaches: the simulated annealing, the mean field approximation of the quantum annealing that I have talked about, then what I call a sparse JASTRO. Okay, we call this JASTRO because it reminds of the JASTRO approximation. Sparse means that, like you have seen in the previous plot, in the previous slide, we have set many of these values to 0. Okay. And then we do the full JASTRO, the dense JASTRO, which is the one where all parameters are assumed to be non-zero. And we go up, in this case, to 150 spins, where the full JASTRO stops because it becomes quite heavy numerically, whereas these other methods can go farther. Okay. But even the sparse JASTRO, thanks to this tuning of the computational complexity. And in this case, as you can see, we are plotting the difference between the energy of each optimization and the average energy on all instances. And you can see that the dense JASTRO, so our algorithm, performs better. Here, lower is better. But you can see that it starts competing with simulated annealing, which is much more efficient to run. It's much faster. And also with the sparse JASTRO. They all start competing here, whereas the mean field approach gives you quite bad results. In this case, there is not a very nice advantage of our approach because, at least this is our interpretation, because this is an all-to-all coupling, and so it's very close to the idea of a mean field system, for which the simulated annealing works very, very well, because it just assumes thermal noise, so it has no structure at all. Let's move on to another model. This is what is called the 3-dimensional Edwards-Anderson model. This means that it's an Ising model on a cube with random couplings, again distributed in a Gaussian way. Okay. And in this case, you can see that, again, the same figure of merit, you can see that our approach, so the full variational method with the two-body correlations, performs much better and scales apparently up to the number of spins we were able to go, scales better than the other approaches. Also, the sparse JASTRO works very well, with the advantage that we can go to larger systems. And whereas both the mean field and the simulated annealing perform poorly. Notice that these numbers are very small. So this is a 1.5% difference between zero. So you may object, oh, but this is nothing. Actually, no, for two reasons. First of all, because of the no free lunch theorem. I mean, even a small advantage can be an important advantage. And second, because you may say, okay, this small advantage, I will keep it for the particular instances of the problem, which are the hardest to solve. Because here I'm not discussing about how hard different instances of the problem are. But there may be some particular instances that are very easy to solve with simulated annealing. And there may be others for which simulated annealing gives a result that is not sufficient for us. And so we may decide to run this other algorithm, maybe 1 times out of 100, only for the most difficult case. And this would give an overall improvement of the quality of the heuristics, which is actually significant and very large. So this is in the spirit of the no free lunch theorem. We want as many algorithmic approaches as possible. And here I show that this is computationally a bit heavier. There is a larger overhead, but it is in a way that scales significantly better than these other algorithmic approaches. For this model, I wanted to show also the histograms of the solutions obtained over a number of instances, that is 10,000 in this case. And you can see that, and I played the game of fitting each of these histograms with Gaussian, okay, just to see how it works. So it seems to work quite nicely. And what you can see is that the blue and red, which are our algorithmic solutions, perform much better on the tails. And this is another good news. It means that the most difficult instances are better accessed by our algorithm, and it's so to say softer variation than by the standard approaches. So we can imagine that we could run this algorithm only for the hard instances 1 times out of a few. Okay, and notice that if this Gaussian fit is reliable, which for the moment we don't know because we don't have enough statistics, it means that the advantage becomes larger and larger as we go to smaller and smaller solutions, so solutions that are better. So this shows that this advantage is not very small, but it's actually quite large if you go in the tails of the distribution of the possible solutions. And finally, I have other two models, the chimera graph, which we did because it's very popular because of D-wave. Again, connectivity, which is given by this chimera scheme. It's the structure of the specific circuit of the D-wave chip. And again, random interactions. And here you can see that, again, there is a strong advantage of our approach, and also of the blue one, which is our approach with a lighter number of parameters with respect to mean field and to the simulated annealing. And to conclude, I have another model which is called it's the planted Ising model. It's I won't go into the detail of the description of this model, but essentially this is a model for which you know how to compute the solution analytically. It's a planted problem, where planted means that you build the model around the optimal solution. Okay, but the algorithms are agnostic to this. So the algorithm don't know that there is an optimal, that we know the optimal solution, and so you can test. And this is why in this case the plot is not with respect to the average, but with respect to the actual minimum. And this problem is built to be hard. So this problem is, if you don't know this structure, then the problem is computationally hard. And what you can see that, again, the ordering of these 4 algorithms is always the same. So the dense variational approach and the sparse variational approach perform significantly better than the other 2 approaches. Okay, and this brings me to my conclusion. So we have used a little bit of insight into the physics of quantum annealing to write and heuristics for the optimization of QUBO problems, which scales, of course, not as well as the simplest algorithms like simulated annealing, but which scales nevertheless acceptably, and where the scaling, so the computational complexity, is tunable through this trick of the sparse entangling operator. And there is a consistent improvement on all benchmarks that we have run. And for me, this can have applications in many situations. But since we have seen that there are hybrid quantum classical algorithmic approaches, so one of the possible applications would be to take the quantum part of this hybrid strategies and replace it with our algorithm, which would run better on a classical computer. And with this, I am finished, and I'm very happy to answer questions. Thank you very much.
Yeah, thank you very much, Vincenzo, for a really nice, informative, and sharing very interesting new results in your talk. Thank you very much. I'm sure there are questions. Anyone wants to start? Please, this is a meeting, so please just unmute yourself and ask your questions if you have any. No rush to ask questions yet, but Vincenzo, you haven't tested anything of these on a quantum hardware yet.
Well, no, because this is conceived not to go on quantum hardware. This is quantum inspired. I mean, this is built to be feasible on a classical computer.
No, I understand, but it could be part of a hybrid strategy. Yeah,
I see. I was thinking of using the hybrid strategy the other way around. So okay. My idea is that in the hybrid strategy, this algorithm would replace the quantum computer.
Okay. So you're not thinking of going in the other direction.
Yeah. Yes. So your divide and conquer, what they call decomposition of the problem is such that you have the master problem that is solved like with one of these standard algorithms like simulated annealing, and then the child problems are run with using this algorithm, which would give considerably better results. So that what was the idea.
Yeah, no, excellent. So, but okay, but there is no lesson that can be learned from this for real quantum hardware.
No, because and we have a lot of ideas. We are at the very beginning of this. So what we are focusing on now is to try and apply this to some problems which are not defined mathematically, but they are rather defined in terms of applications. So we are looking into some constraint problem that can be translated by softening the constraints into QUBO problems. We want to see how this algorithm performs on those. And then, as you correctly noticed, I mean, another thing that we would like to do is to develop a hybrid approach based on this. So to see how this hybridization of optimization algorithms that is now very popular. You can find a lot of literature about this. How it performs if one of the algorithm used in the hybridization is this one instead of the quantum computer. I mean, this one we can go with the dense one up to 200 spins, so 200 qubits, and with the sparse one almost up to 1000. So this is like a quantum computer of okay, yeah, D-Wave does these numbers, but this is a code that runs on a desktop PC. And D-Wave is a big machine, and I'm not even sure that, I mean, it would be nice to make the comparison, as a matter of fact.
No, excellent. And sorry, are there other questions? Please don't be shy. Maybe while people think, Vincenzo, I was intrigued by your generalized atomic coherent states.
Yes.
What other applications do they have?
That's very interesting. Yes, so these are, this is a class of, they can be described in many different ways. This is a class of variational representations that originated from this. Well, first of all, it has a strong connection with what people call graph states, because this unitary here is reminiscent of the one that enters graph states. And parameterized graph states in particular. Here, the additional feature is that you really add this this generality to this generality here, and that's the important feature of the state. It's nice to show that these states can be originate from a group theoretical argument. So you can show that they fulfill a particular property of group theory or of theory of group representation that makes it possible to compute these elements. So there is a beautiful explanation of why you can compute this based on group theory. And there is a paper that describes this mathematical property. The interesting thing is that once you do this with group theory, you can generalize this to bosons. So there is the very same representation for bosons. And but they are very strange. For example, you see this matrix element can be computed efficiently. But if I now, instead of writing this expectation value, I write an off-diagonal matrix element with two such states. So I put here one of these generalized coherent atomic states, and here I put another one with different values of the parameters. You would like to say, okay, this is also feasible. No, it's not. So the feature that makes this computable is so specific that it only works for the diagonal expectation value, and not for off-diagonal. It's quite strange. And it is also close, this ansatz, to a very dense single-layer QAOA ansatz. So if you take the QAOA single layer, but you put all sorts of entangling gates, then you essentially are reproducing this state here.
Okay, that's very interesting. Very interesting. Yeah. I have one last question.
Yes.
I was very intrigued by your Fujitsu digital annealing unit. Do you have one?
No, I don't. No, I don't think they sell it. I mean, they sell the very same service as D-Wave and as other companies. So they say they have a front end with you go there, you pay, you give your problem, the problem is taken, is decomposed. It's there is this hybrid decomposition, and then the child problems are sent to these chips that solve, and then there is another algorithm that solves the master problem, and that's it. So it's the same.
I was hoping it would be like a Raspberry Pi.
No, it's actually I have many at home, by the way. It's not very far, actually. FPGAs are a little bit more expensive. This one must be very expensive because it's very big. The last version does 300,000 binary variables. So, but I don't know how. I don't think they sell it, actually.
But in principle, one could build one with a standard FPGA for a smaller problem.
I think there is I think they designed a specific FPGA architecture. The FPGA part serves to encode the specific instance of the problem, but the architecture is specifically designed to solve Cubo problems.
Okay.
I don't know if they
Interesting.
sell it. Never looked it up. Maybe they sell
I
it.
don't know. Maybe you can check on Amazon.
Yeah.
Yeah. Okay, wonderful. Are there more other questions for Vincenzo? Ilya, do you have any questions? No, Vincenzo, it seems that in the chat there were a few comments. There is a question in the chat.
Okay, let's see.
Is Ziad still here? He can ask the questions. Yeah, you're welcome, Ziad, to unmute and ask your question, please.
Hello, Francesco, Vincenzo.
Hello,
Can you
hello,
hear me?
hello. Hi, Ziad.
Hi.
I'm very nervous. I'm very nervous.
Thank you.
Nobody will bite you.
Thankfully.
Yeah.
So on slide 24, I'm very interested in this probability notation.
Yes.
And
So,
how it presents in this Gaussian distribution.
No, I mean, here it's us. I mean, what we do is that we define a model which we know is hard to solve, to optimize, but these are models that are randomly generated on a computer, and we randomly generate these numbers so that they are distributed according to a Gaussian or normal distribution. So this is a model that we generate randomly to benchmark the algorithm. Then in a real world optimization problem, the actual distribution of these connections is never Gaussian. It's much more complicated. And one of the things that we should be doing is to test the algorithm on these more realistic instances of the problem, and not on these very simple assumptions. But I don't know if this was your question.
Yes, I think it's answering it.
Okay.
And the way that the Wij, I mean, I'm just wondering, are we using square brackets because it's some kind of matrix?
Yes, because it is a
scalar?
matrix. Yeah, I mean,
Right.
all these values are a matrix, but no, the probability is for each of the elements. So perhaps the notation is not very nicely chosen, but you are right. So each of these numbers, so this is a matrix, and each of these numbers is generated according to a normal distribution.
That really, I think I'm understanding it now. So of course, the probability for each matrix is just one number.
Yes.
Oh gosh, thank you so much.
You're welcome.
Okay, Vincenzo, there were a few thank yous in the chat for the very clear and instructive presentation. And if nobody else has urgent questions, Vincenzo, on behalf of all the participants, thank you so much for your time. I think we all learned a lot. We will try to buy a Fujitsu digital unit.
That's a good idea. I would like to buy it myself to test it.
Yeah, no, that would be very cool. Yeah. That would be fun. And and we wish you a good weekend, and I will catch up with you on Tuesday morning. Yeah.
Yes, send me an invite, and we're going to talk. Thank you very much again. It was very nice, and hope to
Thank
talk
you very
to
much,
you.
and we will stay in touch. Thank you.
Yes. Bye.
Bye. Have a good afternoon. Bye.
You too. Bye.
Bye.